Alright, now that we have seen sort of how modules can be used in order to build up larger and larger modules, let's talk a little bit about the overall design process, because what I did over there in terms of walking through a basic ALU was a very ad hoc process, right? It just sort of said, okay, we start with this, we build this, and suddenly we have something that looks interesting. That's not how designs usually work. Normally you want to go the opposite way, right? You start off with some kind of a large system that you want to design, right? And you basically need to go through several different steps in order to get there. Now such large systems, one of the terms that you will keep repeatedly hearing throughout this course and throughout pretty much any kind of career that you have even vaguely related to digital systems, is the word IP, or intellectual property, right? Not a particularly nice term in my opinion, but it is stuck, right? Basically it says that whatever you are designing is a piece of intellectual property, and the idea of that is, this is not actually hardware that is getting built, it's more that this is a description of the hardware in some way. Now technically any program that you write, right, if you write a function in C, that's also intellectual property, but that term is usually not used in the software context, right? It's much more prevalent in the hardware design area, because at the end of the day any kind of modules that you design are usually going to make their way into actual hardware elements that get built, right? So the term IP core is something that we will be repeatedly using throughout the course, and IP core basically means a presumably non-trivial digital design. Okay, you can also have analog IPs, but in this course at least we'll be talking only about digital IPs. Okay, so how do we go about designing large systems? The first thing you need to do is you need to be able to specify what you want, right? And that needs to get refined into a set of requirements. After that you choose a set of components which you are actually going to use in order to build the system that you have now specified and found clear requirements for. You then need to test and make sure that everything works properly, and finally come out with documentation which says, how does the thing work, how can it be used, what are its limitations, what is the scope, and so on. Okay, so what I'm going to do now is take an example and sort of walk through this, but at a somewhat informal level, hopefully give you a flavor of how this happens in practice. But keep in mind that this is not a very rigorous approach to the entire process out here. This is meant more to give you a flavor for how it could happen. Okay, so we start with an informal specification. Somebody comes and tells me, I want a 16-bit up-down counter, right? Now, where might you see such a thing? From the embedded systems or embedded C programming course, you are probably aware of timers, right? And what do timers do? They basically either count up or they count down, and you have the ability to parallelly load a value into the counter, which is maybe the starting point of the counter. And you also have some kind of a configurable threshold which basically says if the counter exceeds this value or it equals a particular value, raise a trigger signal, right? Raise an interrupt or something else which basically says, hey, I reached the threshold, and then decide what to do. You either reset back to the load value or reset to 0 or something, some kind of functionality needs to be there. So it's possible that you are on a team that's building a microcontroller, and as part of that you are assigned the task of build the timer counter, right? Build hardware to do that. So this, as I've said at this point, is still an informal specification, right? The point is it's human centric, it's easy to read. The problem is it's not detailed enough to actually go and actually implement something. Okay, what more do we need before we can start building a circuit? Well, you need a detailed requirement specification, right? One of the first things which maybe you assumed was obvious but actually isn't is what kind of counter. Is it a binary counter in the first place, or is it using some other kind of gray code or some other encoding of numbers that is possible? Okay, now in most cases yes, we mean binary, but it's not obvious. It is something that needs to be clearly specified. Assumptions, right? Making an assumption of this sort and saying, oh, I thought you meant binary, I didn't realize you meant a gray code counter, right, are things that can actually result in drastically wrong or problematic designs, which is why the detailed requirements has to sort of spell out all of these things in sufficient detail that there can be no chance of making a mistake out there. The next question is, are you going to use a clock? Presumably yes, because a counter needs some kind of a state, right? It is evolving from one number to another. So presumably there's a clock. At that point you might ask questions like, is the clock also a digital signal like the other clock signals that are the other signals being used inside the circuit, or is it some kind of an external input which is coming in from somewhere? Maybe I am trying to count the number of pulses that I see coming from cosmic rays in a neutrino detector, right? And this is actually something that had to be dealt with. So is that signal going to be my clock, right? Or is it going to be that my clock is something that I have as a very well defined signal? I only have maybe some other kind of an enable signal that I use in order to decide whether the counter needs to increment or decrement, right? The next question is, how is the and of course the enable signal and the clock are in some sense related, but that also, do you have an enable signal, because that wasn't specified in the informal requirements, right? Should there be a way by which I can just freeze the counter and say, okay, stop counting and wait for something, right? The informal specification said you need to load a value. How is that value going to be provided? Is it a set of 16 bits, right? Or is that only going to be a subset, maybe 8 bits, and you assume that the bottom 8 bits are 0? Or is it going to be that somehow I need to serially load in a value over 16 clock cycles into this counter, which is by itself would make the design quite complicated, right? But it's possible. Let's say I don't have much hardware, I want to do it in a very compact manner. Maybe I might even want to do something of that sort, right? All of these, even though you might think, oh, these are obvious, the point is they need to be clearly specified. Otherwise, you do not have a way of verifying whether the system that you have built matches the actual requirements that the person had in mind, right? Informal specifications leave out a lot of details. Detailed requirements need to specify each of those. So we can refine the requirements, and at this point now we are looking from the point of view of the designer. The designer says, okay, I am going to design a 16-bit binary counter, and it's going to be a synchronous digital circuit, right? I'm going to use the positive edge triggered D flip-flops or something of that sort, right? Keep in mind that at the informal specification you shouldn't even be thinking of things like what kind of flip-flop you are using and so on. But by the time you get to refine requirements, you need to have that information, because now you are almost at the point of choosing your components, right? And I also know these are my inputs. I have a clock input, I have a reset or load input which basically allows me to go back to the load value. I have an enable signal that says whether or not to count. I have a 16-bit parallel bus that gives me the load value, and I have one more input signal that tells me whether to count up or down, okay? The outputs of this module would be the 16-bit value of the counter, and also a trigger signal that basically gets activated whenever my counter value matches with the threshold, right? So by the way, there should also be a threshold value that I need to add over here as one of the inputs. Now I can start to choose components, right? What does that look like? Well, I need a counter. How can I implement a counter? Possibly the simplest kind of counter would actually be to just say, use a 16-bit register, take that register, put it into an adder, a 16-bit ripple carry adder perhaps, right, and add 1 to it and feed this value back. How does this work? Every time there is a clock edge, the value from here goes into the adder, 1 gets added to it, comes back over here. So on the next clock edge, the value sitting in the 16-bit register is incremented by 1 from where it was earlier. So this is a counter. This is actually a very simple and straightforward implementation of a counter. In fact, if you are using FPGAs, this is probably the most efficient way also of implementing a counter. If it's not an FPGA and you are trying to use discrete gates or some kind of application specific custom logic, there may be more efficient ways of implementing counters, but for the present we are just going to ignore that, right? My goal over here is not to sort of go into the most efficient counters, it's more to talk about how I can design this at a sufficiently high level. Okay, now so far so good, but this is just a up counter, okay? What I can do is I can add a multiplexer on this input and say, based on the up down control signal, either feed +1 or -1 into this. Now -1 for a 16-bit value would presumably be in 2's complement, right, such that it actually ends up looking like a -1 and causes this value to decrement on each clock cycle. Okay, great. So what I have is I have a mux over here which basically determines whether it's up or down count. I can also have another mux which appears on the input of the flip-flop, right, and one of the signals to that would basically be the enable signal. If the enable signal is 0, I hold the last value. If the enable signal is 1, I take this, the output of this feedback over here, the +1, and feed it in. If the hold or the enable was 0, I would basically take just this value, which was the previous value of the register, and feed it back directly in here. Okay, great. So I now have the ability to do enable. But that means I can also use that in order to do a parallel load by essentially extending that mux into a 3x1 mux, right? And say the third input basically allows me to load in a value from outside directly into a register. So a lot of the functionality that I wanted has already got implemented at this point. Now comes the question of how do I actually do a comparator. I need to take this output and basically put a comparator, which could basically be thought of as a subtractor, right, which takes control, it takes threshold, subtracts the two, and if it turns out that control minus threshold is negative, right, then it means that, or rather if threshold minus counter is negative, it basically means that the counter has become greater than the threshold. Okay. So it depends on how you are implementing it. If you do counter minus threshold, you would check for MSB equal to 0, which basically indicates counter is greater than threshold, right. If you do threshold minus counter, you would need to do it the other way, right. The point is that all of that is just a question of how you wire it up and how you connect it. So every component of what we wanted at this point can be built based on things that we already know how to design. Do we want to do this using discrete gates? If so, you would need to basically go around searching for the appropriate kind of components, right, counters, registers, adders, comparators, and so on, and wire everything up. You can actually build this on a breadboard and have it working. FPGAs, we'll get to this later, right. Custom chips, you could also choose to actually design a custom circuit that just does this particular functionality, or more importantly a custom IP, an intellectual property that could be used by someone who is actually designing a microcontroller chip, right. So the components basically fall in place and you would be able to get the final design that you wanted. Now we have gone ahead and designed things, right, but before you actually put it out there and say, hey, this IP does what you want, right, buy my IP because I've done a great job of designing it, you need to have something which can convince people that yes, you have actually tested it and your IP does actually work properly under all scenarios. What does that mean? As far as a counter is concerned, there isn't too much complexity, right. Basically what it says is if I give it a clock, it should count. But there are a few test cases. For example, when the enable signal is 0, the output of the counter should not change, right. When the load signal is given, I should find that the output of the counter directly becomes equal to whatever was given at the input. When I switch from up counting to down counting, I should find that the counter basically stops incrementing and starts decrementing, right. I can in other words create a number of test cases and say, okay, if this was the present value and these were the inputs, this is what I should see as the output. That is a test case, right. And what we ideally need to do in this setup is anticipate possible failure scenarios, right. In the case of a counter, the kind of things that are non-trivial would be, okay, what happens if I just turn off the enable signal? It should stop counting. It's not necessarily a failure scenario, but it is a change of behavior from what was happening earlier, right. And okay, it's been idle for a while, now what happens if enable goes from 0 to 1, right. What happens if enable goes from 0 to 1 while the load signal is also high? Should I be counting? Should I not be counting? Should I be stationary, right? Are these things even well defined? You definitely need to have a way of testing and saying, okay, this is how the system is going to behave even if it has not been properly defined, okay. So the testing process is a very important part of the overall design process. It basically tells you that your system is working as expected, right. And what is usually done is we create test benches. In the past, test benches were literally hardware test benches. There would be a bench on which various different kinds of equipment, power supplies, oscilloscopes, logic analyzers would be assembled. Your circuit would be placed over there, connected up and tested. That's why it was called a test bench. For modern digital logic design, everything is virtual. It's all a program inside your computer, but the idea of a test bench remains the same. You need to have a test rig, which basically says, this is your device under test, which is a module that you have created. You need to be able to apply inputs to it, you need to see what its outputs are, and you basically need to be able to say that everything is working properly or not. Okay. Now, the thing about test benches as I have described them over here is, at best you can apply a few different kinds of inputs. But if I look at a counter, there are 16 bits, so 2 power 16 possible states of the counter. There are 16 possible or 2 power 16 possible input values that could be used as the loadable value, right? And there are 2 power 16 different possible threshold values that could be given. I could in principle say, hey, I want you to test every single one of these combinations, and then also add a few more, which is, what about different values of 0 and 1 for the up down, the enable, the load value, and so on, right? And to make matters even more complicated, since these are sequential systems with a concept of state, that is the counter is basically the current value of the counter is the state of the system, it means that the number of possible different variations that I can get is essentially exponentially huge. It's 2 power at least 48, if not larger, right? Different possible combinations that we have, and running through every one of those is essentially impractical. It's impossible, right? For all practical purposes, it's impossible in any realistic amount of time. So what we do instead is we say, let's not be unrealistic here. I don't need to test all possible cases. I probably need to test for a few corner cases, switching from up to down, switching from enabled to not enabled. What happens if I enable while the load is on, if I disable while the load is on, right? All those a few different combinations of that sort, and yeah, I'm good to go, because I don't really expect a threshold of 10 and a threshold of 20 to really make a difference in terms of how the system behaves, right? And that's reasonable. That is what is done in practice, right? You can never really test digital systems through all possible input combinations, because the state space that we are dealing with is just too large. Instead, we make simplifying assumptions and make sure that the tests are as thorough as we can make them. But the problem is, you may not always catch all possible scenarios. Now in that context, that is where the idea of so-called formal verification methods come in, right? Formal methods basically try to apply mathematical proofs of correctness. What they say is, there's a certain specification which is now done in a much more rigorous mathematical sense, and then it says the design that you have created actually meets those specifications in a mathematical sense. What that means is, by doing so, you have actually proved systematically that for all possible input combinations, it is actually going to work correctly. Now these formal methods are not easy to apply and are not always possible to solve for all kinds of circuits. For something like a counter, you could probably even do it in practice, but in general it may not be possible to verify very large designs in this way. However, where they do apply, they are extremely powerful, and it's definitely worth knowing how they can be used. Finally, documentation, the part that nobody likes, or at least designers don't like, right? When you think about it, if you are told your code needs to be well commented, typically the way that people work is, okay, write the code, get it all working, debug it by putting printf statements all over the place, and finally before submitting it, remove all the printf statements, add a few comments. Whether those comments make sense or not doesn't matter, at least they are there, so now it looks like your code is well documented. Unfortunately, that's not particularly helpful, right? What needs to be done is to go through systematically, right? Start off with detailed requirements, maintain proper versions, things like version control. Keep in mind that this course that we are talking about is largely an engineering type of course, right? Even if we look at it as software, it is software engineering, and many of the principles and practices that are followed over there are important in order to really get good systems in place, right? So things like creating detailed requirements, creating versions, updating them properly, and so on is part of the software engineering side of things. Creating proper documentation in the form of data sheets. How do I use a particular IP or a chip that has been designed by somebody, right? What are all the specifications? What are its constraints? How can it be used? When should it not be used? All of that needs to go into the data sheet. Similarly, something that most companies do is they also put out something called application notes, right, which basically gives examples of the usage of certain kinds of chips, right. Let us say you have a counter or a microcontroller, there will be application notes that say examples of the usage of that particular microcontroller, right. And white papers, which are probably a bit more generic than application notes, they sort of treat the problem at a high enough level and say, okay, look, we have studied this problem fairly well, we understand it, and therefore based on this we feel this is how systems need to be designed. All of these are things that you would typically find on the websites of various circuit manufacturers and are well worth reading in order to get a good understanding of how systems are designed and built.